Now we'll study aberrations in lenses and mirrors. Here we can write that defects of images formed by lenses and mirrors are called aberrations. And these are classified, we are talking about aberrations, these are classified in two main categories. These are, we'll study one by one the two. The very first one is chromatic aberrations. And about chromatic aberrations we can write, these are defects, obviously defects in images formed due to dispersion of light by a lens, because of which the image is being produced or images are being produced. If more than one wavelength is there in the light, more than one images will be produced. And here we can write, as mirrors do not exhibit the characteristics of dispersion, so mirrors are free from chromatic aberrations. Here we can also write that all kind of mirrors are free from chromatic aberrations. Let's consider the aberration in lens. If we talk about a convex lens, we can write that its focal length is given by lens maker's formula, which is 1 by f is equals to mu minus 1 by r1 minus 1 by r2. Here we can see that if refractive index increases, the focal length of the lens decreases. When a white light is allowed to incident on the lens parallel to principal axis, then we know well that the mu of violet light, refractive index of the lens for violet light is greater than the refractive index for red light. We can write that focal length of lens for violet light will be less than the focal length of lens for red light. So in this situation, when white light incident onto it, all violet colored rays will focus at a point which we can write as focal length for the violet color, and similarly all red rays will split from the original beam and these will incident or focus at a point which we can write as focus point for the red light, and this was the focus point for the violet light, and the distance of this point from the lens would be fr. And these FB and FR can be easily calculated by lens maker formula by using refractive index for violet and red light. So here you can see, even when a single white light beam is incident onto the lens, several colored focal points will be obtained on the other side of the lens. Similarly, if we produce the image of an object which is white in color or emitting white light by lens, there are several images produced. Here you can see a realistic situation in which you can see for a convex lens, if a white object is placed, a source of light is placed, it produces images on the other side which are spreaded between violet image and red image. It is because of the dispersion of light through the lens, and we can see that lens behaves like a combination of several lenses with several focal lengths, each for an individual wavelength. This is the defect of image formation because of various colors in the incident light, and this is what we call chromatic aberration. Let's continue on the next sheet for the second category. Let us continue our discussion for the second category of aberration, which we call spherical aberration. About a spherical aberration we can write, these are defects in images due to large aperture of lenses or mirrors. This is because if we consider a lens, we already studied that all light rays which are paraxial incident onto the lens will focus at a point which we call its focus. But all other rays which are not paraxial rays, which are also called marginal rays, the rays which are very close to principal axis, we call these rays, we already studied, these are called paraxial rays. And the rays which are away from principal axis, these are called marginal rays. So these marginal rays, due to the radius of curvature of lens after refraction from the two surfaces of the lens will converge at a point which is closer to focus. This is the reason why lens formula or mirror formula is only valid for paraxial rays. If light rays are incident onto the lens or mirror which are away from principal axis, or marginal rays will not converge at focal points. Similarly, when for an object image is produced, there will not be a single point where image is produced. It will be blurred or distributed between few points if we consider marginal rays originated from object. Similar to this, if we talk about a concave mirror, the same phenomena we can explain, like if parallel incident rays are incident onto the concave mirror which are paraxial, after reflection these light rays will converge to a point which we term as its focus. But if we consider marginal rays onto the concave mirror, after reflection these rays will converge at a point which is between pole and focus of the lens. If we consider other marginal rays, you can say these will focus at some other point. So at various points you can simply say all parallel rays will be meeting, and you can say the focus will be spreaded between few points, not at a single point. But if we consider only paraxial rays, there will be a pinpointed sharp focus is obtained. So here we can say for a given point object, point image is produced by a lens or a mirror only when paraxial rays incident from object onto the optical device, lens or mirror is considered. If we consider marginal rays which are incident on lens or mirror away from principal axis, the image produced will also be blurred or distributed between few points. So here we can also write on a note that due to spherical aberrations, a lens or a mirror of large aperture fails to produce sharp image of an object or point image of a point object, and it is due to marginal rays. So if a lens or a mirror is having a very small aperture, only paraxial rays will be refracted from the lens or mirror, and there will be a point image of point object or sharp image of an object is produced. This is the phenomena we call a spherical aberration.